Okay, welcome to the fifth chapter of our course on elliptic operators, and today's topic will be functional calculus. So functional calculus for sectorial operators. You've seen a first instant of a functional calculus last week for the Laplace operator. And the aim of today's lecture is to generalize this to general sectorial operators. So the aim again is to plug in the operator into a function to define something like f of L, but not only for the Laplace operator, but for some sectorial operator. And obviously the way we choose last week, so passing by the Fourier transform, diagonalizing the operator and working with multiplication operators, that does not work. So we have to find a completely new technique to define the operator, but the idea will, the aim is this: define f of L. And what is the idea to do this is going back to complex analysis. And in complex analysis there is a nice formula where you can write a function in a complicated way, and writing easy things in a complicated way is always a good thing in mathematics, because this gives you opportunities to change writing. So what I mean is the Cauchy integral formula. So you can write f of lambda as 1 over 2 pi I times the path integral along some path gamma f of z times z minus lambda to the minus 1. So usually this is written as a fraction, but I write it like that. I want to write it like that. So this is the Cauchy integral formula, which is true whenever this path surrounds the point lambda once in a counterclockwise sense. Okay, and the nice thing about this formula is that at least formally, here you can plug in an operator and at least the things that stand there make sense. So formally, you can write down f of L as 1 over 2 pi I integral over gamma f of z minus L to the minus 1 dz. So the L, for this to make sense, you do not need to plug the L into the function, but only here, and so this is a result. We know how to work with this one. So that is the idea, which seems perhaps a little bit naive, but it works. And that it works is somehow the main topic of today's lecture, to make this precise. Okay, and this idea goes back to the work of Danforth and Ries, who did this for bounded operators. And then this is easier because the spectrum, so you have to, the question is, where do you have to integrate around? So, and it turns out you have to integrate around the spectrum. And for a bounded operator, the spectrum is something compact, so you can take a path that surrounds the spectrum once in a counterclockwise sense, and then you can, for suitable functions f, you can make this work. Generalizing this to unbounded operators was the next step, and the important name in this context is Alan McIntosh. Alan McIntosh will be mentioned several times during the internet seminar. And he was the one who made this idea work. And what I will show today mainly follows the book of Markus Haase, who also did an internet seminar on functional calculus several years ago and wrote the book about this topic that is somehow the main reference today. Okay, so as usual, I start the lecture with some general notation that will hold throughout this lecture, that I do not always have to write it. So again, H is a Hilbert space. Throughout the whole lecture, L is a sectorial operator in H, and I will denote its sectoriality angle as usual by phi L. And the norm on H would be again just written by norm because without an index, but this is not really necessary because you will see today is a rather algebraic lecture. I think there will perhaps be one norm throughout the whole lecture. So, okay. So we can start, and we will do this functional calculus in 2 steps. And first step is today what we call, or what is called the elementary functional calculus. So this will be a first thing, and then we will see that this is a nice functional calculus, but there are really important functions missing, and then we will make it better in the second step and put in as additional functions. Okay. So let's introduce some spaces of holomorphic functions. To make this work, one would imagine that the functions have to be holomorphic or at least meromorphic. And I will just introduce some notations for spaces of holomorphic functions. As we wanted to work with sectorial operators, all this is placed on sectors. So I take some angle between 0 and pi. And then I will denote by h infinity of s phi. So s phi is again the open sector with opening angle, half opening angle phi. H infinity of s phi is the space of all holomorphic functions, holomorphic and bounded functions on the sector. So H for holomorphic and the infinity for bounded. Okay, so this is one space that is of interest. Then there is an important subspace of this one, which I will denote by H infinity 0 of S phi. And that is the space of all bounded holomorphic functions on the sector, with the additional feature that they have some decay at 0 and at infinity. So there is a constant, there are 2 constants, C and S, strictly positive, such that the modulus of F can be bounded by the minimum of absolute value of Z to the S and absolute value of Z to the minus S. And what that means, if you think about it, is the function decays at 0 at least like a power S, and it decays at infinity at least like a power S. So that you have some decay in 0 and infinity. This is this space H infinity 0. And then there is a... The constant is missing. Yeah, you're right. Thank you. Okay. And then there is the so-called Dunford-Rees class, which slightly enlarged this space. So this is the space where we will define the functional calculus by the Cauchy integral formula. And this space is lacking some really important functions that we want to have, and that for which it is really easy to say what f of L will be. For instance, the function constant 1 is not included in there, because the function constant 1 doesn't have a decay at 0 and infinity, but 1 of L should be the identity. And another important function that is missing is resolvence, so 1 over 1 plus Z. This doesn't have a decay at in 0. For Z going to 0, this goes to 1. This goes to 1, not to 0. So it's not included here. But the function 1 over 1 plus Z, we know what the operator is if you plug in L. It's the resolvent in -1. So we want to have these two functions, and that is what we do. We take these functions and add them. So this is what you get if you take the h infinity 0 functions and then just add the function 1 plus z to the minus 1 and the function constant 1. Yeah, and a comment on writing. This is not a good form to write a function, I know. In the lecture notes, we did the trick to say, okay, we will write the function z goes to z by a bold font z. This is bad on the blackboard, so I think on the blackboard I will just do an underlining. So if you see a z with an underline, this means this z is not the complex function z, but it's the function z. Z is sent to z, so the identity function. Why do I do it? Because I will have lots of concrete functions from C to C in this lecture, where I want to plug in the L, and always writing something like, take the map z going to z over 1 plus z squared and plug in L is too long. So I will write z 1 plus z squared of L, meaning take the function that z assigns to z over 1 plus z squared and plug in L. Okay, and the same for the function 1 here. This is not the number 1, this is the function constantly 1. Okay, so, but this is just a matter of notation. What is important is the Dunford-Rees class. So this set here, this vector space E is the so-called Dunford-Rees class. And this is contains all h infinity 0 functions, the constant functions, and all multiples of this particular resolvent. Okay. So to get a little bit more feeling for these spaces, what are typical examples, what are important functions that are in there? So first remark 5.3, some important examples of functions in H10 or in Dunford-Rees class. The function I wrote over there was not just by coincidence, because it's one of the really important examples of an h infinity 0 function. So this is in h infinity 0 of s phi for every angle that you might think of. Because it has a polynomial decay in 0, it has a polynomial decay in infinity, and it's holomorphic everywhere outside of z being minus 1, and this is in no sector. Okay. So this is a nice function, and we will see this often today and on Wednesday. Okay, first important example is this one. Then you might ask, he included this particular function that will give the resolvent in minus 1, so what is about the resolvent in minus 2? So why only this one? And the answer is because if you have that one, you have all resolvents. And that's the next thing to note. So the function lambda minus z to the minus 1. This is in the Dunford-Rees class as long as everything is in the right sector. So the argument of lambda must be greater than phi. So, and why is that? Because you can do some clever rearrangement of things. So this is the function that we want to find in here. And you can rewrite that in the following way. This is 1 plus 1 over lambda times z divided by lambda minus z times 1 plus z plus lambda to the minus 1 over 1 plus z plus 0. So this seems a little bit opaque where it comes from, but somehow it's just checking it. So if you can rewrite this one, multiply numerator and denominator by lambda minus z, and this gives you 1 minus lambda to the minus 1 z divided by lambda minus z 1 plus z. And now if you add up these two, you have z plus lambda to the minus 1 z minus lambda 1 is minus 1 z plus 1. So this gives you z plus 1 over this. So this gives you exactly that one. It's just, as I said, writing easy things complicated is always a good thing. Why is it a good thing here? Because now you see this is a multiple of 1 over 1 plus z to the minus 1. Okay, this is a constant. And this is an H0 infinity function. Why? It's holomorphic everywhere outside minus 1 and lambda, but lambda is not in the sector. And it has a polynomial decay in 0, and it has a polynomial decay in infinity. So what we found is that this function is a sum of an H0 infinity function and a multiple of this particular resolvent and a constant. So it's in the Dunford-Rees class. So somehow it suffices to add this particular resolvent because you get all the others for free. Okay. And then another example that we will see again later is exponential functions. This works as soon as your sector has an opening angle less than pi over 2. So we are strictly in the right half plane. Even with a smaller angle, so the right half less than pi over 2. And then I claim then the function e to the minus tz is also in the Dunford-Rees class for every t positive. It's obviously not an H0 infinity function because in 0 it's 1. So there's no decay going to 0. So a first idea to get this into the Dunford-Rees class would be, okay, let's subtract the 1. So let's take minus 1 plus 1. The 1 is here. But then you destroy the decay at infinity. If you add minus 1, then infinity goes to minus 1, not to 0. So you have to be a little bit more careful. And the right thing is to subtract one of these functions and to add it again. And then again, okay, this is in here. And now one has to think about whether this is H0 infinity, H infinity 0, but it is. The sector is in such a way that that for z going to infinity, the real part of z also has to go to infinity, because the sector has an angle less than pi over 2. So for z going to infinity, this goes to 0 in modulus. Really fast because it's an exponential thing. So for z going to infinity, this goes to 0 with a exponential velocity, so at least polynomially. And for z going to 0, this goes to 1, this goes to 1, and if you do the calculation, you find that there is a polynomial decay. So this is a h infinity 0 function. This is in here, this is in here, so this is Dunford-Rees. But note, it only works for nice sectors less than pi over 2, because otherwise this can explode. Okay. Then, what about the algebraic structure of my function spaces here? And the answer is they are really, really nice. All three of them are really, really nice. I claim that H infinity 0, and the Dunford-Rees class are all not only nice vector spaces, but they are algebras. So this means they are closed under multiplications. And this is easy to see for the first two. Yeah. So if you take two bounded holomorphic functions and you multiply them, you get a holomorphic function and you get a bounded holomorphic function. If you multiply two bounded holomorphic functions that have a decay at 0 infinity, okay, this gives a bounded holomorphic function with decay at 0 infinity. What is not so obvious is for the Dunford-Rees class, because we have this weird sum here, and so what happens if you multiply two of these sums? Oh no. So let's check that. But several things are easy. Yeah? So if you multiply two of these, you end up here. If you multiply two of these, okay, it's easy. If you multiply a constant with one of these, okay, you also stay inside. So there's not too much to check. What remains to check is that if you multiply two of these, you end up in the same. You end up in the algebra. So what you have to check is what happens if you take this function and multiply with itself till you end up in the algebra. And the trick is again to find a good decomposition like that. So, and the right thing here is to write this as minus z over 1 plus z squared plus 1 over 1 plus z plus 0. And this works for all z in S phi. Again, check. So take here 1 plus z in addition, then you have 1 plus z here. This gives you 1 plus z minus z, so 1 over 1 plus z squared. So, and again, okay, this is a constant. This is in here. And then this has to be an H infinity 0 function, but it is, again, it's holomorphic in any sector. It has a polynomial decay in 0. It has a polynomial decay in infinity. Okay. So these are really nice things. They are algebras. There remains the question, if someone gives you a function, a holomorphic function, and asks you, is this in the Dunford-Rees class, yes or no? Yeah, sometimes you can do some little calculations, but it would be nice to have some characterization that tells us if the function does that and that. It's in. Such a characterization is possible, and you find it as an exercise 5.3. And this characterization has a second advantage. It will show that this definition somehow is nice in the sense that also these three spaces are mutually linearly independent. So there's nothing too much. Okay. So now, well, we've not done so much until now. We want to find a rigorous way to define this one. And as I said, the problem will be that for our sectorial operators, which are unbounded, the spectrum of L will be an unbounded set, and we have to do a path integral around the spectrum. And for an unbounded set, around sounds a little bit dangerous. So so the general picture will be the following. We are in the complex plane. We have a sectorial operator. So our spectrum is in the right half plane and inside some sector. So I do the picture for some sectoriality angle that is less than pi over 2. But this will be of no importance. Okay, so we know the spectrum of L is somewhere in the right, in this sector. And now we have to do a path integral around this sector. So first of all, we have to have a holomorphic bounded function on a sector that is bigger. So this is angle phi here. I write the phi here, but this just means that this line has an angle of phi. There will be, I could draw the angle phi here, but there will be much drawn here in here. So, okay, and then what is a good path that at least a little bit surrounds this spectrum in the counterclockwise sense? What we will do is we will take the boundary of another sector. So we will go straight to the 0 and then straight out back. So this will be our path with an angle psi here. And this path, I will also write it down in a formula in a minute, but this path will be gamma psi. Okay, and this path is somehow going around the spectrum counterclockwise sense. This is all this is in the end it's indefinite integral. It's indefinite integrals, so we have to really be cautious and look at convergence and all the stuff. But that's the main idea. And to start things, I assume everyone has seen the Cauchy integral formula in a complex analysis class. The Cauchy integral formula usually is formulated for a closed, nice path, which is of finite length. So it's already a question whether in such a situation you have the usual Cauchy integral formula. And that's the first thing we will prove. Firstly, because we need it later on, and secondly, to give you some confidence that this might work. So the first step is to prove, so this has nothing to do with holomorphic function, this has nothing to do with our sectorial functional calculus. There will be now no operator involved. It's a completely complex analysis result that I will show now. So the situation is as I just did the drawing. So we have a sector of opening angle phi. We have a smaller angle psi, and this psi is greater 0. We have some holomorphic h0 infinity function on the sector with opening angle phi. So the function is holomorphic and bounded all over here, and it has limits, 0 limits, polynomial limits in 0 and infinity. And I will show that for this situation, you really get a Cauchy integral formula. So if you take some point A that is not on the path gamma psi, so it's not on the blue line here, because this is where we want to integrate, and if the in the Cauchy integral formula, the point where you evaluate must not lie on the path. So if you take some A that does not lie on the path, and now you take this path gamma psi that I drawn over there. So how does it look? It's minus t e to the I psi for t going from minus infinity to 0. So what this means is, if you go from minus infinity to 0, this starts at infinity with angle psi and goes down to 0. And then you start at 0 and go up and go again to infinity, but along the line with angle minus pi. And this is exactly what happens in this drawing. You start at infinity with angle psi, you go down to 0, and then for the positive t, you go from 0 to infinity along the line with angle minus pi. So this is this path. And then I claim you have some Cauchy integral formula. So 1 over 2 pi I integral along this path f of z divided by z minus a dz is, and now there are two cases. First case, so this path surrounds this region here, so what we expect is if a is in here, you get f of a. If a is outside, you have winding number 0, then you get 0. Okay, that is exactly what you get. So you get f of a if a is in the sector with opening angle psi, and you get 0 if a is not in this sector, in the closure of this sector. And on the boundary of the sector, it's not allowed to be. Okay, so this is the complex analysis, the result that we need now. And just as I said, to increase our confidence that this crazy idea might work, let's really prove this. And what we do to prove this is we somehow have to get back to the usual Cauchy integral formula. So we have to find a path that is closed and goes around A. The good point is now we are just integrating. The only point of problem is the point A. So A is somewhere in my picture. So somewhere here is A. A or outside somewhere. But what I can do is, what I will do is, I take a huge radius r and close down this curve here. And for technical reasons, let me also take some small radius epsilon here. So this is r, this is epsilon, and then, okay, the path goes like that. Here, here, and here. So this is the path that I will take, and I will do it in such a way that the r is relative to the a far outside and the epsilon is close to 0, and then we will let go epsilon to 0 and r to infinity, and let's see if this works out. Okay, so we choose epsilon and r such that, okay, the epsilon is positive, but doesn't exceed a half of the modulus of a. Note, a cannot be 0 because 0 is on the boundary of our sector, so this is possible. Okay, this is always less than 2 times the modulus. This is not the question, but what I need is that the radius r, the big radius, is at least 2 times the modulus of a. Okay. And then, okay, what do we have to do in order to find that in the limit r going to infinity and epsilon going to 0, this path gives us a length same as the blue? We have to show that the contributions of these two circular arcs goes to 0. So what we look at first is the big radius r. So what happens if you put in the parametrization? Then you get an integral going from minus psi to psi. So the argument goes from minus psi to psi of f of r e to the it. So this is the parametrization of the long red arc here. And then we also put in the parametrization here, r e to the it minus a. Then we have to do the derivative of the parametrization dt. Okay, so that is the contribution of the arc with a radius big R. Okay, so there are several things that drop out in the modulus. So what we do is the evident thing. We take the modulus inside the integral from minus psi to psi. We have an R. This drops out is 1. This is 1. So f of r e to the it over r e to the it minus a. Okay. dt. And now, what is important to note is that now this choice of R plays an important role. So R is more than 2 times the modulus of A. So this is a number that has a radius R, capital R. So no. This number is at least modulus of A. It has a distance of at least modulus of A of this one. So we can estimate this by modulus of A. No, this is the wrong direction. I want to estimate by R. So this is has a distance of R to the origin. This has a distance of at most R halves to the distance to the origin. So these two have a distance of at least R over 2. So this is the one thing. So in the denominator we get R over 2. And here we will use that our function is a h infinity 0 function. So it's bounded. What we here it's bounded, and if you let R go to 0, R to go to infinity, this gives you some additional decay, some R to the s, R to the minus s. So this is just because our function is h infinity 0. If you let R go to infinity, you have a little decay. We don't know how much, but there is some decay in R going to infinity. And this decay is what saves us. And so you see this really, you need the 0 here, the h infinity 0 here. So these two R cancel out, and what you get is 4 c psi R to the minus s, okay, and sending R to infinity, this goes to 0. Okay, so this is the first thing. And the second, the small red thing here with radius epsilon. Basically you do the same thing. So you integrate from minus psi to psi. F of epsilon e to the it epsilon e to the it minus a e epsilon e to the it dt. And yeah, if you do the same estimates, what you get is this is less than 4c psi divided by modulus of a epsilon even to the 1 plus s. So the important point is this goes to 0 when you let drop epsilon to 0. Okay, but what does this mean? This does mean that the Cauchy integral theorem that we want to check, so this is this one. So integrating along gamma psi, the blue line, f of z divided by z minus a dz. So I want to write this as a limit r going to infinity and epsilon dropping to 0 of the same thing along this red curve. So gamma psi epsilon r. So this is this blue-red curve there. So our bounded curve over the same integrand. Okay, but how do I justify this equality here? This can be justified by just seeing or noting that this integral is an absolutely convergent integral. And why is it an absolutely convergent integral? Because if you do a modulus here, you can again estimate this by some constant times some decay in infinity. A little bit of decay in infinity plus 1 decay in infinity gives you 1 plus a little bit of decay in infinity. And this is enough to make it absolutely convergent. So this is an absolutely convergent integral. So this limit is okay. But now this is an integral for the usual Cauchy integral formula. So this is now a nice closed piecewise C1 path in the complex plane, surrounding A or not surrounding A, so you know what happens. So you know what comes out. So this is the limit for r going to infinity and epsilon dropping to 0 of either f of A or 0 if A is in S psi and 0 if A is not in the closure of S psi. Okay, but now and we're done. Okay. So this gives at least a little bit hope that the crazy idea up there might work. So at least for complex numbers we can do a Cauchy integral formula in this unbounded setting as long as we integrate h infinity 0 functions. For just bounded holomorphic functions, at least this proof goes wrong and you cannot do it like that. But for h infinity 0 functions everything is okay. So let's try to make this work. So our hope is put L in place of A. So let's take a psi that is in between the sectoriality angle and our phi. Take some function f that is in h infinity 0 of the sector with opening angle phi. And then what we want to do is take this integral here and take an L instead of an A. Okay, writing it again as a result. So the first thing we have to check, does this integral remain absolutely convergent? And this works fine. So if you do an integral over R of the thing with, now we have to put in the L of H norm. This is an integral. This is now an integral in the, if you put an L instead of A here, you're integrating in the vector space, in the normed space of bounded operators on H. So it's a Bochner integral then. And I want to show that this Bochner integral is absolutely convergent, so I put in the norm, and I get f of the path times the resolvent along the path, gamma psi of t minus L to the minus 1, times the derivative of the path, L of H dt. So this is the thing we have to show that it's finite. If we have that this thing is finite, then this is will be an absolutely convergent integral, and at least we can write it down, and there is some result. So then, by this integral, we can define some operator, and then we have to show that this gives something meaningful. Okay. So what happens here? Let's put in everything we know. If you do the estimate, what do you get? Okay, the first thing is, so this is a complex number, so you can take it out as an absolute value. So then you have this resolvent. This also is a complex number that you can take out as an absolute value. And the even nicer thing is this gamma psi of gamma psi prime. So where is the gamma psi? Gamma psi is up there. If you do the derivative, this gives you just e to the I psi, or e to the minus I psi. You derive with respect to t. So this derivative has modulus 1. So modulus of this thing is 1. Okay, this is not too complicated. And what remains is the operator norm of this resolvent, but now we know that our operator L is a sectorial one. So we know the operator norm of the resolvent can be estimated by a constant, which is here, times 1 over the modulus of gamma psi of t, dt. Okay. So this is the resolvent estimate for sectorial operators. The constant is not here, the constant is here. And okay, so we have these two parts of the path. So let's take these apart. This gives on the one hand f to the t I psi plus f to the t e to the minus I psi. Okay, and what is this? So what is the modulus of gamma psi of t? Gamma psi is just t times some phase, so this is t. Okay, and now you see we exactly have again taken the right choice in taking h0 infinity, because these two give you, this behaves like 1 over t to the s infinity, and it behaves like t to the s in 0. It has a polynomial decay in infinity, it has a polynomial decay in 0. You have a 1 over t. So in 0 you have a 1 over t to you have a 1 over t to a little bit less of 1. In infinity you have a 1 over t to a little bit more than 1. So it's exactly the thing that you need for absolutely convergent integral. So this is fine. Okay, so we indeed have an absolutely convergent integral in the space, in the Banach space of bounded operators on H. So this means this integral, so what this integral gamma psi f of z, z minus L to the minus 1 dz is absolutely convergent in L of H. So there is some limit. One thing that one still has to check, but this follows from Cauchy's integral theorem in L of H, is that all this construction does not depend on the angle psi. We chose some angle psi between the sectoriality angle of L and phi, and somehow the psi might influence the result. It does not, as usual for these Cauchy integral theorems and formulas. And not important where exactly the path is, but that it nicely surrounds the problematic points. So, but once one has checked that, we can now define what we mean by f of L. So this is definition 5.5. Take again some angle that is greater than the sectoriality angle. Take some function f that is holomorphic and vanishing in 0 and infinity on this sector. Then choose some angle psi that is between phi L and phi. So you can do this in function of the phi. We know the result will not depend on psi. And once you have that, then you can define f of L just by our Cauchy integrals. So as 1 over 2 pi I integral over gamma psi f of z, z minus L to the minus 1 dz. We know this is an absolutely convergent integral, so it will converge to some operator, and this operator we call f of L. So this means we have defined an f of L for all functions in H 0 infinity. We want to have f of L for all operators in the Danforth-Ries class. So let's for the moment hope that we in the end can show that our functional calculus will be a linear thing. So that f plus g of L is f of L plus g of L. So that means the only thing that we still have to define is what happens with the functional calculus on the constant functions and on the function 1 plus z to the minus 1. Okay, but that's not difficult. That's we know how to define this if everything works out fine. So let's do it. So again, take some phi between the sectoriality angle and pi. Now take some function the Dunford-Rees class. Then we can write this function f as a part in h0 infinity plus some constant c times the function 1 plus z to the minus 1 plus some constant d. So here h is a h0 infinity function and c and d are complex constant. So every function in Dunford-Rees class can be written like that. And then what you do is you set f of L being h of L in this sense plus, okay, what happens with this function? Okay, this gives you z 1 plus L to the minus 1 plus d. If this works out rightly, then it has to be this definition. So let's try this one. Okay, so and what that gives us, what this gives us is again, or is some map, not again, it's some map that takes every function in Dunford-Rees class and assigns to this function this operator and goes into the bounded linear operators on H and assigns to every function this function f of L. And this map will be called the elementary sectorial functional calculus of L. I put the sectorial into parentheses because in this course we will only look at the sectorial functional calculus for sectorial, so there is no need to distinguish many functional calculi. You've seen one more, you've seen the one for the Laplace operator next week, and it will be one of our tasks to show that these two definitions give the same. Because at the moment, for the Laplace operator, we've defined 2 times in 2 different ways f of minus Laplace. So this could be a problem, but we will see it's not. But apart of that, we will only deal with this functional calculus, so we will usually drop this sectorially. Okay. And the thing that we will do next is to, as I said, we will see it fits well to the functional calculus we had for Laplace. But the other thing is we have to study the properties of this map. We want it that this is a nice map. As I said, for instance, we want it to be linear, for instance, and other stuff. But before we do that, one really important warning, because this is often a source of misunderstandings when you see a functional calculus first. This writing f of L is a very suitable thing, and it's nice because somehow it's a notation that captions what is done. You take the operator, you plug it with the f. You have some operator f of L. But there is one slippery slope that you mustn't get on, and that is to think of this as a function f with an argument L. Because the L in all this stuff is a fixed thing. So we fix this in notation 1151 all in the beginning of the lecture. So the L is a fixed thing. What the functional calculus does, it takes the fixed L and plugs it into different functions. So the map that is behind the functional calculus is this one. So in some sense, this is the other way around as you are used to. So the L is the fixed thing and the variable thing is the f. So the f varies and the L is fixed. So please do not think of this as a function f of various operators that you can put in it. That's not what functional calculus is. Functional calculus has a fixed operator L and puts it into different functions. This is So if you see f of L, you have to think of it as this map, and not the map that L maps to, that L is mapped somewhere. It's not the L that is mapped. That's why this notation is a little bit dangerous. But you will see that this notation is the right thing to do it, because this gives a nice calculus, and you can. It's very intuitive. But this is a thing to really they take a fine point on it. It's the F that varies and the L is fixed. Okay, so I think this is a good moment to do a short break and then to continue with the properties of phi L. Yeah, let's start again and tackle the two things that we will have to do for this lecture. So the first thing is to show that our functional calculus, now defined for every sectorial operator, is consistent with the functional calculus that Moritz introduced last week for the specific negative Laplace operator. And then we will look at properties of our functional calculus. But first, let's check that we didn't define the same thing twice in different ways. We defined it in different ways, but let's show that it's the same outcome. So look at the special sectorial operator minus Laplace. We know on Rn, so this is the operator of lecture 4. And this is sectorial of angle 0, so we can take any angle phi strictly positive. And let's take some function f in the Dunford-Rees class of S phi, and somehow we have to make sure that the f of minus Laplace defined in lecture 4 is the same as f of minus Laplace defined now. And now I thought to write it down. I will take these two things apart in notation with this a little bit sloppy writing, but what we want to show is that, so by this I mean f of minus Laplace defined in the sense of lecture 4, the same as f of minus Laplace defined in the sense of lecture 5. This we have to check. So how was f of minus Laplace defined in the fourth lecture? So if you look back to 410, the main thing was to see that by the Fourier transform, the Laplace operator was equivalent to some multiplication operator with a very easy multiplication function. So m of xi was just modulus of xi squared. And then the idea was to say, okay, if we have this, we know how to do functions of multiplication operators. So you take f of the negative Laplace operator as Fourier to the minus 1, and the multiplication operator with the multiplier f applied to m. And then we saw that this works out fine. So, and now we have to make sure that we get the same result with this way as with our way by the Cauchy integral formula. So we have a function in Dunford-Rees class. Remember, the Dunford-Rees class has 3 building blocks. So it's the h infinity 0 functions. It's the multiples of the function 1 over 1 plus L. And it's the constant functions. So the constant functions are easy. Yeah? So if you take the constant 1 function and plug in minus Laplace in this sense, this gives you the multiplication operator with the constant 1 function. This is the identity. And the identity is also what you get if you take our definition, because this was just by definition. On the constants we had put 1 of L equals identity. Okay, and the resolvent also is fast. So if you take the function 1 plus z to the minus 1, now remember this means the function z is assigned to 1 plus z to the minus 1, and you plug in minus Laplace in the sense of the 4th lecture. This gives you, on the Fourier side, the multiplication operator with 1 plus m to the minus 1. And now we know how multiplication operators with inverses are calculated. This was long ago, but this was in the first lecture, 1.16, which tells you that this is 1 plus the multiplication operator with m to the minus 1. Okay. And this means putting the minus Laplace operator in this function in the calculus of chapter 4 gives you the inverse of 1 minus Laplace. Because this is the multiplication operator of minus Laplace. Okay, but this is the same. So this is 1 plus L to the minus 1, and this is f of L. Okay, also this works out. Both give resolvent, as it should. So as one would expect, the complicated part is the biggest building block of the Danforth-Riesz class, so the H infinity 0 functions. So what happens there? So take some H infinity 0 function on our sector, and then for technical reasons, let's first argue for very nice arguments. So take some u in the space, in the Schwarz space, such that the Fourier transform of this function, which is also in the Schwarz space, is not only Schwarz, but even a test function, CC infinity. Okay, and for these arguments u, calculate h of L u and then the Fourier transform. So this h of L is now in the functional calculus in the sense of today. Yeah? Okay, so let's plug in the Cauchy integral formula. So this is 1 over 2 pi I integral over gamma psi. Psi again, an angle that is greater than the sectoriality angle, so greater than 0 and less than phi. H of z, z minus L to the minus 1 applied to u dz. Okay, then, so the Fourier transform is linear and it's a bounded linear operator on L2. This is an integral in L. This is now an integral in L2. We have an argument here. So, and by what is in the appendix on the Bochner integral, for the Bochner integral, you can pull in bounded operators. So we can pull in this Fourier transform inside the integral. So this is 1 over 2 pi I integral gamma psi. H of z is a complex constant, and then you get the Fourier transform of z minus L to the minus 1 u dz. So, and now this is nice because this we know in the functional calculus of our minus Laplace operator from the last lecture. So this is 1 over 2 pi I integral gamma psi h of z, and then this gives you the multiplication operator. This gives you z. No, it gives you the multiplication operator with z minus m to the minus 1 applied to the Fourier transform of u. Because Fourier to the minus 1 m u hat gives you exactly this. And so if you apply Fourier here, you get that. Okay. So this is now an equality. This is now an equality in L2 of Rn. And the tricky point, and that's why I started with this really nice function here, is that somehow now I want to see this as a pointwise inequality in Xi, almost everywhere. And you had this discussion already in the last week with Moritz. So when can I pull in the Xi? You write of xi here, you write of xi here, and then you want to pull it inside the integral. When can you do this? One way that is described in the appendix, if you can do this, seeing this integral not only as an integral in L2, but also in a space of continuous functions on a compact set. And this is what is possible here now, because this is a continuous function, and since the support of U hat is compact, you can have a continuous function on a compact set. So you can pull in the xi the same way as last week, and this gives you that h of Lu hat at xi is the same as 1 over 2 pi I integral over gamma psi h of z, and now putting the xi inside z minus m of xi to the minus 1 u hat of xi dz. And the advantage now is that now we have a complex integral, just a complex integral. And we are integrating along a path gamma psi, some complex function h of z multiplied with this one. So this is again a Cauchy integral formula. So you can just apply our lemma 5.4 from the beginning of the lecture, where I showed you the complex analysis Cauchy integral formula for these weird paths gamma psi. And this gives you just this function where m of xi is put in as z. So this is a constant for z. You can take it out. So this gives you h of m of xi u hat of xi. So and now use that the Schwartz space and CC infinity are dense in L2. So in the end you get for all L2 functions u that h of Lu, so I take an inverse Fourier transform, h of Lu is the inverse Fourier transform of h applied to m times u bar, u hat Fourier transform. But just by definition of the functional calculus last week, this is h of minus Laplace. U. And we've seen that h of L and h of minus Laplace is the same. Okay, so this was task number 1. So we've now defined a nice sectorial elementary functional calculus, and the one that we had as an appetizer last week is just a special case. And this will, on the long run and during this lecture series, this will be somehow the starting point to generalize things that whenever you can do something with the Laplace operator by doing a Fourier transform. So the Fourier transform is a really strong thing to get to know things about the Laplace operators, because you can Fourier transform. This is an easy multiplication operator. You can handle this, you can find many things and translate them back to the Laplace operator. And in some sense, one of the philosophies of this lecture or this course is that by replacing the Fourier transform with functional calculus, you will have a tool that gives you the same possibilities not only for this special Laplace operator but for any sectorial operator. So the functional calculus is for the sectorial operators the tool that you need to replace the special Fourier transform that works for the Laplace. That is somehow a philosophy that will come up again and again in this course. Okay, so one final result for today, and this is now what are the algebraic properties of our functional calculus. At the moment we know that this functional calculus, given the operator L, for every function f in the Dunford-Rees class assigns to f some bounded linear operator. And we want to know that this assignment somehow fits well to the calculation rules that we know for functions. So you can add functions, you can multiply functions, and we want to see that this behaves well, and the result is everything is nice, which means that this is a good tool. So take again some angle phi greater than the sectoriality angle. Then we have defined our functional calculus phi L. So this phi L gives for every f in the Dunford-Rees class some f of L. And I claim that this phi L is an algebra homomorphism. This phi L goes from the Dunford-Rees class, which is an algebra, to the linear operators on H, which are an algebra. So it's the best thing you can have. It's an algebra homomorphism. It translates every calculation rule from the algebras to the other one. So this means, written out more in detail, that for every f and g in the Dunford-Rees class, and for every complex scalar lambda, you get that the stuff is linear. So if you take a linear combination of two functions and you plug in L, this is the same as plugging L into f and g and doing the linear combination in the operators. And you have multiplicity. So if you multiply two functions in the algebra in the Dunford-Rees class, note we showed this is again in the Dunford-Rees class, so you can plug in the L, and the result is this is the same operator as if you first plug in L into f and g and multiply them or concatenate them in the algebra of bounded operators. Third thing, furthermore, I will show one special equality which we will need often. I take again this function z over 1 plus z squared. You've seen this already as an example for an H0 infinity function, and why this function is so important will become clear on Wednesday. We will use this very, very often. So this is an H infinity 0 function, and so I can plug in L, and the question is what comes out. There is a naive idea which should come out, and a good usually for functional calculus, if you have a naive idea what should come out, you can be confident it will come out. So this will be L times 1 plus L to the minus 2, but we will prove this. And what we get from all this in particular is that whenever you take two functions and you look at the corresponding operators after functional calculus, these two operators will commute. Why? Because f and g commute in the Dunford-Rees class. So if you multiply two complex functions, f times g and g times f is the same. So f of L, g of L is f of g L, is g times fl is g of L f of L. So this comes immediately from this one. Okay. This means that the image of phi L always is a commutative subalgebra of the Dunford-Rees class. Okay. So let's prove this. First thing, okay, I claim that it's linear. Yeah, this is more or less by definition. It's a little bit cumbersome to write it down because you have to, for f you have to split it into the three parts and then the g, and then but somehow these three parts is linear. The Cauchy integral is linear. Everything that is involved is linear. So this is just writing it down. A little bit more tricky is the multiplicativity. Multiplicativity. Yeah. This word is too complicated for me today. Okay, multiplicativity. Because what you have to do, what we will do is we will start on this side here. We will look at f of L, g of L and show that it's f times g of L. So we have two f of L and g of L both expand to a Cauchy integral. And we have to deal with the product of these Cauchy integrals. Or even more. So if f and g are both h infinity 0, we have to deal with the product of the integrals. But f of g could be in other parts of the Dunford-Rees class. But as we know already that the stuff is linear, we can reduce this to several cases. So one case is easy. If f and g are both constant functions, then this is true, because this is constant. This gives constant times constant. Okay. If one of them is a constant function, this also is true, just by linearity. So if either of these is a constant function, you can take it out by linearity and everything is okay. So these cases are easy. What remains? So we have to check that for 3 cases. So the first case is f and g are both in the main building block of our Dunford-Rees class. The second case is one of the two is the special resolvent that we had, and the other is in the Dunford-Rees class. And the third case is they are both the resolvent. The rest of the cases involves a constant, and for the constants it's clear. Okay, so these 3 we have to check. Okay, and I will start with A and then look how much time we've left and do B and C. So let's first do A. Both are in the h infinity 0 space. So now what is the picture? We have again our spectrum somewhere in the sector. We have the sectoriality angle phi L. We have the angle phi where the function lives in the sector sigma phi. And then what we need is to define f of L. We need a path, a sector path that is a boundary of a sector with some angle psi. So this is gamma psi. But now we also need a path for the function g, and it's a good idea in this case to take a path that has a different angle, and we will take for the function g a larger angle. So this is gamma nu. But still nu less than phi, obviously, because otherwise the integral is not defined. So we take an angle psi that is greater than the sectoriality angle, and an angle nu that is even bigger but below phi. And then let's calculate what is f of L g of L. And this is both our Cauchy integrals. So this gives you 1 over 2 pi I squared, because there are 2 of them, integral gamma psi, integral gamma nu, f of z, g of w, z minus L to the minus 1, w minus L to the minus 1, dw dz. So in fact it's 2 of these integrals and I already stuffed them all together. Okay, so this is what is f of L g of L, and now we have to show this is f g of L. And the main ingredient that you need for this is the resolvent identity. Here you have a product of 2 resolvents. This looks very much like the resolvent identity. So let's use it. So what do we get? Okay, I keep this 1 over 2 pi I squared. I will not make the I squared a minus 1 because this 2 pi I will soon separate again. So then we have gamma psi, gamma nu, f of z, f of z, g of w. And now from these 2, from the resolvent identity, you get a w minus z, and then here you get a difference of the two, so z minus L to the minus 1 minus W minus L to the minus 1 dW dz. Okay, and now we can split this into two integrals. This is now bad for the blackboard, but okay. So this gives, now we make two integrals. So the first one with z minus L to the minus 1, and the inner integral remaining the W integral. So we take everything outside the inner integral that has only a z to it. And that gives you a 1 over 2 pi I integral gamma psi. Then there is the f of z, which has nothing to do with W. Okay, I put the second 1 over 2 pi I here. Then you have the integral gamma nu. The f of z is already here, but you have the g of W divided by W minus z. And then there is the z minus L to the minus 1, but this does also not depend on W, so the W integral is finished here. Z minus L to the minus 1 dz. Yeah, this is the first one. This is the one that you get from this one. And now we have a second with this factor. And in this integral, we will do a Fubini theorem, so we will change the order of the two integrals and do the same stuff as before. So this gives you minus 1 over 2 pi I, now integral gamma nu. Then you get here the g of W. You have 1 over 2 pi I integral gamma psi, f of z, W minus z dz, W minus L to the minus 1 dW. Okay, now it's good to make a close look to these inner integrals. These are now pure Cauchy integral formula integrals. And they are purely complex. There's no operator involved here. This is now complex analysis. And it depends now whether the z, let's look, if the z is inside this path, then this gives you gamma of z, g of z. If it's outside, this gives you 0. So the z is on the path with angle psi. So here at the image, at the drawing, you see the path with angle psi is inside the sector with angle nu. So the z is inside this sector. So this gives you a g of z. This gives you a g of z. What happens here? Here you have a W that is on the path gamma nu. So the W is on the green path. You integrate along the blue line. This is outside the sector, so this gives you 0. Okay, so this integral, the second one vanishes. And we are left with 1 over 2 pi I integral gamma psi f of z. This gives you g of z. Z minus L to the minus 1 dz. And what was just a huge mass of a formula immediately becomes what you want. Yeah? It's rarely that it goes this fast. But what you have here is f times g times the resolvent, 1 over 2 pi I. This is just f times g of L, just by definition. So it's just, the point is to look carefully at these Cauchy integrals here. So this was the case A. So let's look at the case B, which is the case where f is just the resolvent, so f is 1 plus L to the minus 1, and g is given, g is a h infinity 0 function, so here we have to write down a Cauchy integral. So this is 1 over 2 pi I gamma psi f g of z, z minus L to the minus 1 dz. So this is by definition of the functional calculus. F is 1 plus z to the minus 1, so this is the corresponding operator. G is in h infinity 0, so this is the corresponding operator. And we somehow have to prove that this is the same as f times g and then plugged in L. So, but again, we have a bounded operator before a Bochner integral, so we can plug it in. And this gives us 1 over 2 pi I integral gamma psi. G of z is just a complex constant. 1 plus L to the minus 1, z minus L to the minus 1 dz. And again, the winner will be the resolvent identity. But now you have to, there are several awful minus signs not to forget. So the best thing I think to see it is to write this as minus 1 minus L to the minus 1. So let's make 4 minus signs out of 1. But then you have the usual form of the resolvent identity. So I'll keep that minus in front here. Then you have gamma psi. Okay, G of z divided by z minus minus 1, so z plus 1, times, and now the difference of the two, minus 1 minus L to the minus 1 minus z minus L to the minus 1. Okay. Now, this minus sign is nice because if you put it in again, all these other minus signs cancel out. So, we have plus everywhere. And if you look at it, now, again, make two integrals out of this. So it's more or less the same idea. You make two integrals out of this. This gives you 1 over 2 pi I integral over gamma psi G of z over z plus 1 of 1 plus L to the minus 1 dz plus the second 1 over 2 pi I integral gamma psi G of z divided by z plus 1, and the other one is z minus L to the minus 1 dz. And now this can be taken out of the integral. This is does not depend on z. So what is this? This is again a nice Cauchy formula integral. Our lemma phi 4 minus 1 is not in the sector. Minus 1 is clearly not in the sector. Minus 1 is somewhere here. So this is 0. Okay, and what is this? This is just the integral that defines the functional calculus for the function g divided by z plus 1. And note, since g is in h0 infinity, this gives an additional decay at infinity, so this function is in h0 infinity. So this is really the right definition. So this gives you g divided by 1 plus z of L, which is nothing else as fg of L. So this is the second case. In the second case, you also have f of Lg of L is fg of L. And we are left with the third one. So in the third one, f times g of z, both in the third case, f and g are both the function 1 over 1 plus z. So this is 1 over 1 plus z squared. Okay, and this is not a nice function to calculate what is the function, what is fg of L, because it's not in h infinity 0. So it's not so easy to see what comes out. So let's again do such a trick to expand it in 3 parts. So this is, I claim this is 1 over 1 plus z minus z over 1 plus z squared. Just do the calculation. This gives 1 plus z over this squared, 1 plus z minus z is 1 plus. Fits. Okay. And now the good thing is, we've seen this function 270 times already. We know this is in h0 infinity of s phi. And this is an elementary stuff of our Dunford-Rees class. Okay, so we know what we find if we do fg of L. So this means fg of L minus f of L g of L is now just by definition, what is this? By definition, this is 1 plus L to the minus 1 minus, let's call this again h. So minus h of L. This is the problem to know what is this, what is h of L. Minus f of L g of L is clear, is 1 plus L to the minus 2. Okay, and this is now do some algebraic, add another identity. So minus h of L minus 1 plus L to the minus 2. So this gives 1 times 1 plus L to the minus 2 minus the same thing. So what you get is L times 1 plus L to the minus 2 minus h of L. So what you need to show that this is the same as this is to show that plugging L in here gives you this function. And this is exactly the furthermore claim that I made up there in the theorem. So what you need for the third part is just this equality. So what you need is that if you take z over 1 plus z squared and plug in L, this gives you L times 1 plus L to the minus 2. And once you have this, we finish the thing. Okay, and this can be shown. So what's the time? Okay, so it's in some sense it's the part where you need the most complex analysis. So what one does is one puts, in the end one finds a Cauchy integral formula for derivatives, because you have a squared here. So you play it back to the Cauchy integral formula for derivatives, which is also mentioned in the appendix. And then this gives you that it works out. Okay, but I think there's not enough time now left, so I refer to the lecture notes where it's done, and we'll then next lecture on Wednesday we'll continue with the second part of this chapter, which is about regularization, which then again will extend our functional calculus, because we now have a huge class of functions that we can put our operator in, but there are still functions that are really easy, and we do not know yet what it means to put the operator in. For instance, the function z going to z. It's obvious which there should be. This should be L. Or the function z squared. This should be L squared. But at the moment we cannot do it. Note that for all operators in the Dunford-Rees class, for all functions in the Dunford-Rees class, f of L is always a bounded operator. These are not bounded, so this will not work. But we want to have these functions too, so we see the need to extend our functional calculus, and to extend it also to unbounded closed operators, not only to we must allow that f of L is unbounded operator. And this is the topic of Wednesday's lecture. Thanks for listening, and see you on Wednesday.